Are you ready? Wrestling fans, are you ready? For the thousands in attendance and the millions watching around the world, from the capital city of the United States of America, Washington, D.C., ladies and gentlemen, let's get ready to rumble!
All right, now for the main event, the mean value theorem. Okay, one of the most significant results of elementary calculus. Okay, again, this will be a duh theorem, but it actually does have ramifications. Okay, we'll see it actually bridges the gap and helps us to do the second part of calculus that we're going to learn this year. All right, but the mean value theorem states this. Suppose that the function is continuous on the interval AB, closed, differentiable on the interval AB, open. So the same two conditionals of the Rolle's theorem, it does not have the third. Okay, very important, it does not have the third. F of A and F of B could be anything. But if it's continuous and if it's differentiable, then what the mean value theorem says, that there exists a number C, an element of AB, so somewhere in between A and B, such that the derivative evaluated at C is the same thing as F of B minus F of A over B minus A. All right, so if you'll notice, this part over here, the F of B minus F of A over B minus A, that is your slope formula. That's just another way of saying y2 minus y1 over x2 minus x1. Okay, so it's slope, derivative of slope, so it kind of makes sense. But visually what we're seeing here, go back, it says if I've got a function, okay, here you got a curvy function here. I got A and I got B. Notice F of A and F of B are not exactly the same. All right, well, if I take the line in between those two endpoints and find their slope, that's called a secant line. If I find their slope by saying F of B minus F of A over B minus A, I found the slope of that line. What the mean value theorem guarantees, and there exists at least one point, could be two, could be three, could be more, there will exist one point in between A and B so that its tangent line has exactly the same slope. And that's what we see over here. Okay, this point right up here, excuse me, its tangent line is parallel to the secant line, so that means that its slope is the same as the secant slope. Okay? Now we won't get into the full proof of it. You can probably look at some of that in your book. All right, but basically what it does, all right, is it takes this graph where F of A and F of B are not the same. Let's see if I can do it here. All right, and it tilts it. Okay, it just takes the graph, and my board is giving up on me right here. All right, it takes it and it tilts it. All right, applies a weird kind of transformation. Again, you can see exactly what in the book. So that F of A and F of B are actually the same thing. It turns this line into basically zero. And then Rolle's theorem applies and says, hey, I've got a point up here where the slope also has to be equal to zero. It takes it and tilts it. Okay? It does a little Google when you Google in askew. It takes the whole page and shifts it. Okay? Does a little tilt to it. Also try to do a barrel roll in Google. You won't be disappointed. All right? But that's what mean value theorem is. And it makes sense. You can see it visually that that is going to happen. So let's look at this example here. Find the value of C, satisfying the conclusion of mean value theorem for an interval 0, 2. All right, the two things we need to make sure that it does work before I do the conclusion is this thing continuous? Not printing? Is this thing continuous? All right. Yes, because it's a polynomial. All right, it's differentiable for the exact same reasons. It's a polynomial. All right, so we need to do a couple of things in order to do it. First thing we need to do is find the derivative. F prime of x. Easy to do here, 3x squared minus 2x minus 1. Simple enough. All right, and then we need to set this derivative evaluated at c. Okay, because remember the then part of mean value theorem was that f prime of c is equal to f of b minus f of a over b minus a. All right, so what we need to do for this problem is we need to say the f prime of c, so basically rewrite your derivative, but put a c in there. So 3c squared minus 2c minus 1. Mean value theorem guarantees that there's some solution to this if this is equal to the f of our endpoints subtracted over our endpoint subtracted. So the f of 2 minus the f of 0 over 2 minus 0. All right, so I'll rewrite my 3 squared minus 2c minus 1. I'll figure out what f of 2 is by plugging into the original problem. The original, not the derivative, but the original. If I plug a 2 in, I get 8 minus 4, which is 4. 4 minus 2, which is 2. And 2 plus 1, which is 3. So I get 3 minus, I plug a 0 in. I get 0 minus 0 minus 0 plus 1, so 0. All over 2 minus 0. Oh, did something wrong there. I'm sure you're yelling at me and saying, stupid Mr. Wilbanks. All right, but when you plug a 0 in, I'm sorry, might have said it right. 0 minus 0 minus 0 plus 1 actually gives me a 1. All right, and then I'll evaluate that out. So I got 3c squared minus 2c minus 1 is equal to 3 minus 1 is 2, divided by 2 is equal to 1. And then from there, it's algebra. Okay, solve this out. Bring everything to one side, so if I subtract the 1 over, that gives me 3c squared minus 2c minus 2 is equal to 0. All right, and then can we solve that out? Okay, give you a second while you solve that out, making sure I've done everything correctly to this point. All right, will it factor? All right, I don't believe so. So we are going to have to use the quadratic formula again. All right, which will say that c is equal to a negative negative 2, so plus 2, plus or minus the square root of negative 2 squared, so 4, minus 4 times 3 times negative 2, so it turns into a plus 24, all over 2 times 3, which is 6. Clean it up a little bit, 2 plus or minus the square root of 28, all divided by 6. 28 is the same thing as 4 times 7. All right, so it comes out as 2 plus or minus 2 squared is 7, all over 6. Which if you divide a 2 out of all the constants and coefficients, you get 1 plus or minus the square root of 7, all over 6. So there's actually 2 places on the graph where I have that slope of 1. All right, but there's only one of them going to be in the interval. 2 of them could, but it's not going to happen in this case. All right, because the minus, the square root of 7, Well, I'm not exactly sure what that is. All right, but it's somewhere between 2 and 3, because 2 squared is 4 and 3 squared is 9. So 1 minus that's going to give me a negative number, so I can kind of ignore that one. And so the one I'm looking for is the plus one. All right, mean value theorem said it had to work. All right, so 1 plus the square root of 7, all divided by 3. It should have been 3 there. All right. Oh, if y'all are in class, y'all would be hopefully telling me that I made that mistake. All right, so if I do that, 1 plus the square root of 7, all divided by 3, that does in fact give me approximately 1.215. All right, so this one right here, 1 plus the square root of 7 divided by 3, or approximately 1.215, is that C in between 0 and 2 that's guaranteed to have that slope of the secant line at that point. Mean value theorem guarantees it. All right? So, again, that was the illustration. You'll have to do it. Okay, but not really totally the main point. Many of the most important results in calculus, including one we call the fundamental theorem of calculus, follow from the mean value theorem. All right? For now, we'll derive a result essential to the second half of calculus. How many functions share the same derivative? All right, a couple of theorems before we get there. Suppose that the derivative of a function is 0 for all x in some interval. Then f of x is a constant on I. All right? What that says here is that all of these functions right here have a slope of 0. Okay? Over the entire interval. Okay? But those functions are all just constants. Okay? For example, this line up here is the line f of x is equal to 3. The blue one here is f of x is equal to 2. The green one right here is f of x is equal to negative 1. All right, and the orange one looks like it's negative 4, so f of x is equal to negative 4. All right, pretty much if the slope is 0 everywhere, the derivative is 0, then my function is constant. Notice there's several of them. There's actually an infinite number of solutions, but those functions are all going to be constant functions. All right, the corollary, which means it follows directly from that, all right, says almost the same thing, okay? Except it's not just a derivative of 0. All right, it says if two derivatives are exactly the same of functions, all right, then those functions are either exactly the same or they're the same as the other function except for some constant added to the end. Okay, so notice all these functions are parabolas. Okay, their derivatives will be exactly the same thing because their slopes are all exactly the same at the same points. All right, but the functions are all different. But they're really not. Okay, they're all 2x squared minus 3x, except one of them has a minus 1, one of them has a plus 2, and one of them has a minus 4. Okay, they're all the same thing except for some constant. All right, so that brings us to this problem right here. Find all functions that have a derivative equal to 3x squared plus 1. All right, so if our derivative is 3x squared plus 1, all right, what we're wanting to do is go backwards here. What function would give me this derivative? All right, and hopefully by now we have enough experience with the derivatives to realize what would happen. Okay? When we take the derivative for power rule, we bring the exponent down, okay, and we subtract the exponent by 1. So the original function here, before we took the derivative, would have to have x to the third power, because the 2 would have to go up to a 1, to go up by 1 to a 3, in order for the derivative to bring it down. And since it's just a 3 out in front, that means there was no coefficient in front to start with, because the derivative of x cubed is in fact 3x squared. All right, we take care of the 1 part. If something has a derivative of 1, that means right before it we had just x, or a 1x. All right, because the derivative of x, you just take it away and leave the constant. All right, so there's one function that has that derivative, but to find all of them, all we have to do is say, you know what? That corollary to that theorem says, you know what? If this is true, okay, if this derivative comes from some function, it's going to be this function, but it also could have some random constant out at the end. So all we have to do here is say, work backwards a little bit, find the function that did give me this derivative, and then add a c to it. Because when you take the derivative of a constant, it just goes away, so it would not show up in the derivative. All right? And then we've actually done what we call anti-differentiation, which we'll talk about come January and February. Okay? And mean value theorem is used in the proof of that previous theorem and corollary. All right, and I believe, let me make sure. All right, that is all I have for you today. Work these problems, and I'll see you next time.